Hello, this video is going to cover geometric sequences. So let's look at what are these kind of sequences. What they are is they have a starting value and a common ratio. So starting value and a common ratio. And everyone's like, well, what's a ratio? It means you're a common thing that you're multiplying by when you move up the sequence. Um, so you're basically multiplying by something for it to be geometric. So let's look at our two recursive and our explicit formulas. We'll start with recursive for specific geometric sequences. So we again have to display one. We're going to call the first spot A, or we could just say question mark, either way, but let's call it A. That's our first one. A to the n, it's equal to the number before times my ratio. So R is going to be the ratio. And that's basically what you're timesing by each time that you move up. And it's got to be a constant. You got to move up by the same number. And we'll look at obviously some examples in just a second. What about the explicit? So the explicit formula would go A to the n is equal to A1 times R to the n minus 1. Okay, so what am I saying? Oops. Explicit is A1, first term, times R, that ratio, to the n minus 1. I'm saying, okay, as you move up on your terms, right, you're going to have that ratio being like squared to the third, to the fourth, to the fifth. And so that ratio will be multiplied multiple times as you go through. And that's our explicit formula for them. So let's look at an example. So what if I have 3, 6, 12, 24, and 48, however we want to go. So here's our formula. We'll do a couple things. First of all, is it geometric? We'll be asked that on a couple questions in your homework. So you go, okay, what is my common ratio? So the way we look at the ratios is we go the number before, the 6, or the term before, divided by the term before it. So 6 divided by 3, which we can see is 2. The next ratio would be 12 to 6. Ratios are comparing two things. The next one would be 24 and 12. So let's divide these all out. Do they equal the same number? 2, 2, 2. So this all is 2, which would be our R, or our ratio. It's going up by R of 2. Okay, so that's kind of cool. And our starting number's 3. What about looking at this one and writing it as recursive? Okay, so recursive, our A to the 1 is going to equal 3. So our first number is 3. And then our A to the n is going to equal A to the n minus 1 times R, which we found is 3. So you're timesing the one before by 3. And that's it for recursive. I'll do explicit over here. So explicit would be, for this one, it would be A to the n is equal to A1, which is 3, times the ratio, which we said is 2, to the n minus 1 power. So you're going to multiply by, oh, I did 3 over here. I was like, wait, we're going up by 2's. So our ratio was 2. Why did I think it was 3? I'm not sure. Maybe because it started with 3, but we were going up by 2's. So we have to times by 2 the number before. And then it's going to be 2 to the power. So think about this. If I want to get the third term, I better get 12. So I would go 3 minus 1, which would give us 2. 2 squared is 4. 4 times 3 is 12. Because we had to times twice, or 2 squared by the 2. So that's kind of how the power one works. Let's look at this. This one's a little bit challenging. So what if I had my sequence is 3 to the 5th, 3 to the 10th, 3 to the 15th, and then 3 to the 20th. So it's a little confusing that what you're going up by, but we can kind of see that the exponents are going up by 5, so you can kind of see the pattern. But let's look at this in terms of, is it geometric? And if it is, let's do our two formulas in this with these weird looking ones. So the way we figure out if it's geometric is we take the one before, the 3 to the 10th, we divide it by 3 to the 5th. Then you have to remember that when you're dividing, it's like I have 5 on the bottom, 10 on the top, and 5 are going to cancel with 5 of them on top, or you subtract those exponents. So this one's going to give us 3 to the 5th. Let's see if we get 3 to the 5th for the next ratio, which would be 15 over 10 for the exponents, which we can see again would subtract to the 5, which does give us 3 to the 5th. And the last one to check is 3 to the 20th over 3 to the 15th, which again, all of the ratios would reduce to 3 to the 5th power. So that's our R. So if I went to write recursive like I did here, I'd say a to the first is 3 to the 5th, and I would say a to the n is equal to a to the n minus 1 times 3 to the 5th. And that's kind of confusing because you have 2 3 to the 5ths, the first one and your ratio. Okay, so then our a to the n for the explicit would be our first term, which was 3 to the 5th, and then we're going to times it by 3, we're going to times it by 3 to the 5th, and then it's going to be an n minus 1 up here. So let's see if we did this right with the n minus 1 times the 5. So we want this third term. So 3 minus 1 is going to give you 2. 2 times, or 3 minus 1 is third term. Yeah, 3 minus 1 is 2. 2 times 5 is 10. Oh, I see where my... So we have 3 to the 10th times 3 to the 5th. So you would add the 5 and 10 to get the 3 to the 15th. So when you're multiplying, you're adding those exponents. I forgot about this extra one. I was like, wait, I only get to the 10th. Okay, so there is a kind of harder one. I did want to show you in the book one thing that they kind of walked through, and then we're going to learn one other thing here in this section, but they kind of walked through the physics behind this ball bounce. They said, okay, well, what if I gave you the first ball bounce, but not the second, and then I gave you the third? How could we then logically work through this problem? So the knowledge that we know is the first term is 100, the second term is 49, and they did tell us this is a geometric sequence. So we do know those. You can use the explicit formula to relate A1 and A3 and to find R. So this is how they thought of it. A to the n is equal to our formula here. So if I did a to the 3, it's equal to 3 minus 1, or r squared. And then they put in the 100 here, and then they put in the 49 here, and then they solved this. So they got out our R. What is the relationship between them? So all they did was know that our general formula, if I put in a to the third, the 3, okay, and then I substitute, I can get back to the ratio or the R, and then I can write the general formula and work on other parts of it. But I kind of wanted to show you a problem where they walked through using that third term and that first term. Here's the other thing they kind of cover is this geometric mean, which I have now taught 3 different ways in 1 week. It's funny because this curriculum I teach all 3 courses out of it, and they all 3 teach the same topic differently. So this is the geometric mean. This is not the same as the mean in the arithmetic sequences because those ones were a regular mean where you add and divide by 2. These ones are different because you're timesing by something. You're not adding as you go up. So it's a lot harder to find the mean because we're not averaging. So the geometric mean of, let's say, x and y is plus or minus the square root of x times y, which by far is probably the easiest formula I've seen. Either way, the geometric mean, you times them and square root them. Okay, and it could be positive or it could be negative of that. So that's the other little bit tricky thing that it throws in there. So let's look at where would I use this geometric mean. Well, I would use it if I know the first term is 48, but I don't know the next term, the second term, but I know the next term is 3. So I have to be timesing by something to get down to that 3. So here's how I can figure out what that is. I would say, okay, it's going to be positive or negative, the square root of the 48 times the 3. The mean, the geometric mean between these two numbers would get us the middle number. Again, geometric is going up by the time, so it's a little bit different. So I'm just going to do 48 times 3, which is going to give me 144. And the square root of 144 is 12. So keep your plus or minus, and it's going to be positive or negative 12. Why do I have both positive or negative? Because if it's negative 12, then you're multiplying by a negative 12 each time, and every other one would be positive. Well, we don't know if that's negative or positive. So you have to include both negative and positive on this one. So if this one was negative and this one was negative, then we'd know this had to be positive. Because if you're multiplying a negative in there, you would get a negative times a negative, and it would give you the positive, and then you'd get a negative, and then you'd get a positive. So know that the pattern can go negative, positive, and that kind of brings in that second term. Let's see. Let's do another one that was harder using the same concept. So if I know 972, but I don't know, let's just call them X, Y, Z, and the last one's 12. However, they always use like little highlighted blank spaces in some of the programs and in this book. But so we have 3 terms missing, so we know the first and the fifth term. Well, we can use the geometric mean between these two to find y. So we know that y is going to have to equal the positive or the negative of the square root of 972 times 12. So that's a big old number. So 972 times 12, yes, I am definitely using my calculator, is 11,664, and then I'm going to square root that number, and I get 108. So y is equal to positive or negative 108. So let's see. Now we know y. We can use our 108 geometric mean with 972 to find x, because x is going to equal the plus or minus square root of 972 times 108. Our answer we got in the problem before. So 972 times 108 is a big old number. And then I'm going to square root the big old number, and I get 324. Right? And now, last but not least, is this z. So we know z is going to equal the positive or negative square root of y, which we know is 108 times 12. So 108 times 12 is going to give me 1,096, and I square root 1,096 and I get 36. So there, and then it could ask you, well then what would be the sequence? Well, for this one, the sequence could be 972, keeping them all positive, 324, 108, 36, 12, and then the pattern would continue, Or the pattern could have gone 9, 72, negative 324, positive 108, negative 36, positive 12. Every other one would be negative. Okay? So either one could be our answer. And that's kind of as hard as it'll get, is using that geometric mean to find those missing pieces on your sequence.